Hello and welcome to the INQA seminar series. Today with us we have Yoshihiro Nambu from INQA AIST, and he's going to tell us about error correction in quantum annealing. Please begin.
Thank you very much, Mr. Chairperson. Hello, everyone. Thank you very much for joining this seminar today. I'm Yoshihiro Nambu in the NEC AIST lab of AIST Japan. It's my great pleasure to have the opportunity to talk about my work on this online seminar. Today, let me introduce my work entitled Error Correction of Parity-encoding-based Annealing through post-readout decoding, which was published on arXiv last month. Okay. Now, this is the outline of today's presentation. The purpose of my presentation is to show how the post-readout decoding works in the parity encoding scheme, which is known as Lechner, Hauke, Zoller architecture in quantum annealing. First, I will talk about important techniques for near-term quantum annealing, that is error correction and embedding. Next, I will explain syndrome pattern, which is an important notion in the error correction. Then we explain the scenario considered in my paper, that is two-stage hybrid computation comprised of map decoding in the first stage, that is annealing, and APP decoding in the second stage, that is the post-readout decoding. Finally, we explain two examples for two-stage hybrid computing. The first one is a quantum annealing correction, and the second is a parity encoding. Okay. Let me explain error correction for realizing near-term quantum annealing as first technique. Challenge is that quantum annealing devices are affected by the coherence, noise, and control errors, which makes them particularly interesting for study of tailored practical error correction techniques. Two scenarios are reported to achieve this. The first is a quantum annealing correction and related techniques. The other is a parity encoding scheme, which is called LHZ architecture. Okay. The working principles for these reported as follows. The first one is energy gap protection by boosting, which protect physical information from errors. The other one is a post-readout decoding, which recovers logical information encoded in noisy physical information. The other technique we consider is embedding, for embedding logical information into physical information for quantum annealing. Here, the challenge is that since near-term quantum annealing hardware has limited connectivity between qubits, we require techniques that enables to embed logical problem into the available physical device connectivity. Two schemes are reported to achieve this. The first one is minor embedding and related techniques, where a logical spin is mapped. Okay, where a logical spin is mapped to mutually interacting chains of ferromagnetically coupled spins. The other one is a parity encoding scheme, which enables imperfections, implementing logical spin systems via planar lattice of forward coupled spins with local interaction. This table shows the current status for these required techniques. The minor embedding can use only for embedding. Okay, minor embedding can use only for embedding. By contrast, QAC, quantum annealing correction, can be used only for error correction. Therefore, we need to use the combination of minor embedding and quantum annealing correction to achieve both error correction and minor embedding simultaneously, which makes system very complicated. By contrast, parity encoding is expected to be the technique that can be used for both error correction and embedding simultaneously. However, the post-readout decoding method has been established for the QAC, that is majority vote decoding. It has never been established for parity encoding scheme. And the overhead is much larger for the PE system, probably because of lack of efficient post-readout decoding method. This view graph shows the formulation of error correcting codes. We consider linear block codes with message of length large K, length with large K, as a set of Boolean variables from U1 to UK. We call this source word. The source word is supplemented with redundant check bits and forms code word U, C, code word C. The check bits satisfy parity check. The code word satisfies. Okay, sorry. The code word C is represented by bipolar sum of the components of the source word U. The check bits, these check bits satisfy parity check equation represented by the constraints. And for bipolar sum of the component of the code word. Here, bipolar matrix G and part H are called generator matrix and parity check matrix, and satisfy this matrix equation. This source word U and the code word C are represented by Ising variable as large small z, large z and small z, large z and small z, corresponding to logical spins and physical spins, as shown here. At the same time, these equations are converted to the associated equations, as shown here. Where additive equation are replaced with multiplicative equations for small z and large z. In the next view graph, we note that the variable s, which is a function of physical spin variable z, small z, and defines parity check equation. A set of variable s, I, z is called syndrome in the theory of error correcting codes. We call this set of large S and for arbitrary physical spin state Z a syndrome pattern. If Z contains no error, then all the elements of the associated syndrome pattern should be 1 because of the parity check equation. Such as state Z is called code state. If Z is not code state, then it contains some errors. If we define error patterns as efficient element-wise product of Z and Z prime, as shown here, it is easy to see that the syndrome pattern for Z prime is only a function of error pattern E. Z prime is a function of error pattern. Because of this functional relationship, we can infer error pattern E from the associated syndrome pattern. This syndrome pattern, which is discussed later. We should note two facts here. First, syndrome pattern is a classical analog of independent commuting generators of the stabilizer group in quantum stabilizer codes, which are simultaneously diagonalizable and measurable. Next, the syndrome pattern is not unique. This means that we can consider many SZ whose elements are mutually independent, because we can consider many independent equations consistent with parity check equation here. Two different syndrome patterns should be mutually related. That is, we can consider different syndrome pattern, all the elements of which can be expressed as products of element of original syndrome pattern. Example will be shown later. Okay. In this presentation, we consider two-stage hybrid computation. At first stage, arbitrary initial state Z prime is prepared for physical spins in the non-code state. In the first stage, we develop the state dynamically by the Hamiltonian model computation and obtain the state that minimizes the Hamiltonian. This readout state R gives the inferred state of target state from the viewpoint of maximum a posteriori decoding, map decoding. However, R may contain errors with respect to the target states. In the second stage, we recover the correct inferred Okay. In the second stage, we recover the correct inferred state by majority vote decoding, which is a posteriori probability decoding given by Massey. We repeated this calculation many times and obtained the statistically best inferred state. Okay. Let us first consider next the first stage. In the first stage, we use map decoding, which is base statistical inference of target states. The map decoding can be written by two representations. First is the one written in terms of the logical spin variables. In this case, we infer the logical state Z star using the knowledge of J that is regarded as a false physical state that contains errors and likelihood based on the Bayes theorem. Likelihood. Okay. And the problem leads to minimizing the Hamiltonian of these logical spins. Okay. The other one is one written in terms of physical spin variables. In this case, we infer the physical state small z star using the knowledge of J that is equivalent to the false physical state and the likelihood based on the Bayes theorem. And the problem leads to minimizing the Hamiltonian of logical spins. Okay, physical spins, Hamiltonian of minimizing this Hamiltonian of physical spins. And we should note that in deriving this Hamiltonian, we need to consider informative prior for physical state Z, which originate from the parity check constraints, as well as a knowledge of likelihood. As a result, we have extra Hamiltonian that works as an energy gap protection, which approaches zero if Z is cold state. And next, we consider the second stage, that is a post-readout decoding. This part, second stage. For the post-readout decoding, we effectively use correlation between the syndrome patterns and the error pattern stated before. In this case, we can infer error patterns by analyzing the associated syndrome if having weight for false state Z prime is small. Here we should note that the number of -1 in error pattern is Hamming weight. That is a distance from a cold state. Massey considered APP, in other words, threshold decoding in his thesis. He showed that the error pattern E can be inferred from the syndrome pattern for the readouts R using the knowledge of the associated marginal probability, this probability. He modified his theory, and he also showed that the physical state, not the error pattern, physical state, Z can be inferred from the syndrome pattern for the readouts R using the knowledge of the associated marginal probability, this probability. I must introduce the concept of the orthogonal syndrome pattern A. Orthogonal syndrome pattern A, which can be derived from any syndrome pattern S. This original syndrome pattern can be converted to this orthogonal syndrome pattern. He showed that the required marginals should have values larger than 1/2 if we use A instead of S, arbitrary S. In other words, the error pattern E and the orthogonal syndrome pattern, error pattern E and the orthogonal syndrome pattern A should have reasonable correlation if noise is small to a certain extent. Using this result, we can infer the error pattern E by majority voting. Majority voting for the syndrome pattern A. That is derived from the syndrome pattern S. He also introduced a modified pattern B here that can be derived from the readouts R and the orthogonal syndrome A, syndrome pattern A. For pattern B, we can derive this equation. That this product and this product should be equal, so that the inferred state Z and the pattern B should have reasonable correlation. Thus, we can infer the physical state Z by majority voting for the pattern B that is derived from the syndrome pattern, original syndrome pattern S. Now let me show you two examples. First is the quantum annealing correction. In the quantum QAC, quantum annealing correction, classical repetition codes are combined with Ising spin systems. This figure shows one realization of QAC. In this system, we consider K replicas of N network of N Ising spins characterized with the same intra-replica connectivity coefficient, Jij. And every spin associated with the same index I is adjacently coupled by intra-replica ferromagnetic interaction, which offers energy gap protection given by this penalty Hamiltonian. In this case, the associated syndrome pattern is given by like this. Because adjacently coupled replicas are only adjacently coupled, a syndrome pattern should be have k and k plus h indexes. Okay. Alternatively, one can another realization of QC given by this figure. In this system, associated syndrome pattern is given by like this. And which can be represented by the products of this syndrome pattern. Evidently, two syndrome patterns are related. That is, every element of S is given by a product of elements of S prime. In this case, orthogonal syndrome pattern A should be S, this S. That is in this case, okay, and which gives pattern B like this. As a result, base optimal estimator of I's physical spin is given by majority vote of the readouts of I's spin in every replicas. Optimal estimate is a majority vote of say readouts having the same spin indexes, index I in every replicas. This is consistent with our general belief. The related topics is the simulated quantum annealing and the finite temperature decoding uses similar scheme. Okay. This view graph explains why orthogonal syndrome pattern is useful in the majority vote decoding. To obtain the correct inference, we need to make a fair majority vote, not just a majority vote. I believe that the key point is that the fair voting is ensured by using orthogonal syndrome pattern. In the interest of time, in the interest of time, I would like to omit further explanation beyond this. Please refer to master's thesis and my paper for further details. Okay. Next important example to be explained is parity encoding. The Hamiltonian of this physical spin is given in terms of physical spin variables, small z in Zoller's papers as like this. Okay. Zoller shows this scheme have this Hamiltonian in 2005. In this case, here the associated random syndrome pattern is wait for product of spin variables as shown here. Now we consider the majority vote decoding for this system. Orthogonal syndrome pattern is considered to be shown this, which is weight 3 product of spin variables. And this A is a function of this S. For example, this component element can be rewritten as this product. Okay. From this, associated modified pattern B should be like this. And finally, Bayes optimal estimator for IJ's physical spin variables is majority vote showing like this. And using this majority voting, we can achieve the fair voting. To see the result of majority vote decoding, we represent the state of the configuration, state or the configuration of the physical spins, Z, by symmetric bipolar matrix as shown here. This component is a copy of this component. So this matrix is a symmetric one. For example, target physical state, that is a ground state of Ising spin Hamiltonian characterized with this coupling matrix is plotted here. And example of readout state is shown here. By calculating element-wise products, we obtain the error pattern shown here. Then the majority vote decoding can be written as some matrix operation shown here, which is a matrix multiplication and taking a sign of this one. In this view graph, we show the evidence of robust majority vote decoding for parity encoding. To see this, we consider matrix operation shown here. Here, the function Fn is n times iterative matrix multiplication of Fr. We show typical results for error pattern associated with two readout states for two different coupling matrices. Matrices for n equals 0 indicate error pattern of readout states, and its associated weight for syndrome pattern. This one. We calculated error patterns for inference Zn by using this equation for increasing n values. The result is here. And n equals 6, we achieve error-free state. We see that the inference G star n approaches error-free matrices as n increases. This is observed for wide variety of false readout states. Thus, we conclude that this offers a robust majority vote decoding for parity encoding spin system. This is a conventional majority vote decoding scheme. It uses a random spanning trees for majority vote decoding. In this case, fairness was ensured by randomization of spanning trees. Fairness was ensured by randomization of taking spanning trees. And very large number of random spanning trees should be generated for fair voting. Thus, it is inefficient. On the other hand, because our decoding method doesn't rely on randomization, it is very efficient. This view graph shows the result of Monte Carlo simulation. It shows what readout states contributed to the correct inference. This distribution shows the probability that the readout states becomes a code state, becomes a code state, and target physical ground state by map decoding. As a function of two weight parameters, beta and gamma, which is weight of problem and penalty Hamiltonians. If we note the 2 point A and B on weight parameter space, we see that the target physical state can be obtained only for point A. Target physical state can be obtained only for A. This is reasonable because the target physical state should be code state. So the at point B, we cannot obtain any physical target ground state. Okay. In contrast, this big graph, the distribution here indicates the probability that the inferred state agreed with the target state by majority vote decoding after map decoding. In this case, we can obtain correct inference for point B, where we can obtain only non-code readout state after map decoding. Non-code state readout. Non-code readout state. And in this case, the efficiency of successful inference was 400 times efficient. 400 times larger than the map decoding. These results suggest that the non-code but correctable state, readout states contribute to correct inference by majority vote decoding. If confirm this suggestion by investigating the spectrum of readout states contributed to the correct inference. This figure shows the spectra. These figures show the spectra of the readout states and decoded logical states. If we set parameter is at A here, then these red beans indicate the contributed readout states for map decoding without majority vote decoding. their spectra are consistent with the expected ones. In contrast, the green beans here indicated the contributed states for majority vote decoding after map decoding. The spectra indicates that these contributed readout states are indeed non-code but correctable states. Okay, this figure shows the spectra of the readout states and decoded logical states. If we set weight parameter at point B here, from the spectra for these contributed readout states, we confirm the previous conclusion. We can see that the best number of correctable states, contributed to the correct inference of the target states. This two-stage hybrid computation might be efficient because the number of correctable states is very large compared to the target ground states. The ratio of states is very large for these correctable states because these states are excited states. And the other reason we consider is that since majority vote decoding is a deterministic algorithm, it doesn't matter the potential barriers presented in the map decoding. Okay. As for the second reason, our two-stage hybrid computation can be considered as realization of soft annealing concept proposed by Zoller. He considered that in a larger dimensional space, it is possible to go around barriers to find the minimum. Optimization easier in the large space. In the interest of time, I would like to omit further explanation beyond this. Please see this link for further details. Okay. Now we want to summarize. We found that majority vote decoding is certainly effective also for parity encoding if fairness is considered appropriately. And efficiency is largely enhanced by introducing majority vote decoding after map if annealing parameters are selected appropriately. And robust majority vote decoding scheme was proposed. We should note that to achieve these results, for body that is high weight coupling is crucial for its realization. The open question is how robust is this hybrid computation? That's all. Thank you for listening.
Yeah, thanks for your talk. So let me ask a question just to sum up what I think I understood. So you propose a new way of decoding the results of error-corrected quantum annealing, right?
Yes.
And
Yeah.
do you make any comparison between this way and what people did previously in terms of the success probability?
Previous reports means QAC or the
Any previous work, but what I'm
any
interested in is
previous.
to see a success probability of your method on some
Yeah.
problem compared to the success probability of another method on the same problem.
Not. I don't yet. So it's a next next problem. Yeah.
Yeah, thanks. So if there are no further questions, then um, thank you for listening and see you all next week.